to introduce our speaker, Hanno Sandler, who comes from New Zealand, and he's going to tell us all about how to make robots work in education. Let's give a big hand.
Hello. Can everybody hear me? Mostly? Yes. Okay. So, I'm Hanno, and lived in Germany for a while, and here in Cupertino. Went to Stanford, did startups, and moved to New Zealand with my family about 5 years ago. And always a big highlight of my trip back here is to come to the HBRC group. I also belong to the KiwiBots group in New Zealand. We've been shaken up a little bit with the earthquake, but we're still around, and would love to see some of you guys out there, or good place to visit. Okay, so I always talk about my projects, and the list is getting longer. We'll see where we go next year. So I have two kids, a 5 and a 6-year-old, and they're starting school, or actually in school. In New Zealand, on your 5th birthday, your present is a backpack, and you head off to school. So I have two kids in school, and so I'm very excited to spend a lot of time at their school and at other schools around Christchurch, getting kids interested in science, technology, engineering, and math. I'm working on a robot curriculum. I'll talk about that. I showed off Viewport. It's this debugging tool, lots of real-time graphics, and Visual Studio-like trace debugging for our microcontrollers. 12 blocks was the visual language I introduced last year, sort of similar to Scratch and App Inventor, but lots of power, refactoring functions, and integration with ROS and Skype and everything. T-Bot is going into production tomorrow. I have unit number 1. There have been about 35 made so far, but they're now coming off the assembly line, so we no longer have to do them one by one. And PropScope is the USB oscilloscope, which I collaborated with Parallax. I did the firmware and software, and very nice now is that it's $199, so it's something you can buy for a student or get them excited. And it also comes now with a 350-page book that takes you from very simple DC measurements to AC, to sine waves, to op amps. So someone wants to learn electronics. Parallax is very much known for education, and this combines the hardware, some pieces, and the software and the book all together. And then I published one book, I think 2 years ago, for the Parallax Propeller with some other people. That was all sorts of projects. I wrote about my computer vision guided balancing robot that could dance with kids. And I'm now writing another book to be published by Elector and Circuit Seller on advanced robot technologies. So a lot of things that I'll talk about today. We're targeting them to all the way down to kindergarten, primary school level with the curriculum, but I'm also writing books at the advanced level for advanced engineers on building advanced robots. And I'm also working on cool projects like America's Cup. 2 years from now, San Francisco, they'll have very big, very cool looking catamarans, and I'm working with the New Zealand team on their entry to that. So a lot of cool projects. Okay, so let's get into the talk. Computers are getting smarter. Deep Blue, that was a long time ago, but not too long. Watson was earlier this year, and so obviously computers all around us, and as time goes on, there'll be even more of a factor in all of our kids' futures, in terms of programming, in terms of using them, in terms of making sure that everybody's getting the most of what they're doing. Tech education needs a boost. Yes, most schools have a soldering iron, or they have some wiring projects that they can do with kids. But as a whole, there's a lot to be desired in terms of making things very approachable, making them very tangible, and making them concrete so that kids can identify with it and have a lot of fun with technology. As a whole, we're talking about STEM. It's the acronym: Science, Technology, Engineering, and Math. And what you need here is a very solid foundation of technical concepts. There's the infamous Barbie, math is hard, right? And some of these subjects are hard because they're abstract. I have a very smart son and daughter, but it was still very difficult teaching basic math concepts. It's very easy to point at something and say, this is a flower, and then the brain does something and regurgitates, that's a flower. And counting is very easy too. 1, 2, 3, 4. But now coming to more abstract things, this is 5 plus 5 is 10, and 8 plus 2 is also 10. That gets more abstract. And then the more you get abstract, the more difficulties most people have with those concepts. Students typically learn by doing, and probably all the engineers here learned by doing. They didn't learn it by reading it or by watching someone, but you learned it by playing with Meccano, or playing with electronics, or getting started by programming something and seeing some hurdles and then getting past them. Throwing clay on a pottery wheel. There's no way you can learn this by watching someone else do it. You just have to do it and have to get your fingers in there and figure out how hard to squeeze and how much pressure to apply. Same thing with math and science and engineering, and you really have to get in there and do it. How is STEM currently taught? Well, you have algebra classes, you have math classes, you have biology, and a lot of these, increasingly so, these are going where there's a textbook, there is a person who's writing something on the board, and people aren't experimenting anymore. They're not getting the 101 chemistry experiments, but it's very safe, very orderly. Go look on the board and step by step follow what I'm doing. A lot of people think that robots can bridge this gap. So it's another application of robots besides moving things around or doing pick and place. But maybe robots can help students learn, can help kids get excited about what's out there. And what it does is combine the hands-on learning, so giving kids something that they can touch, something that they can play with, something that they can add on, they can claim, this is my own, I've built this, and these abstract concepts that I've talked about. So learning how to do math, learning how to do science and experimenting and having a hypothesis and then going from there. So robots can provide a very rich learning environment where you have lots of sensors, where you have programming, where you have modules that you can add on and go from. This is a lots of text slide, I'm not going to read it, but there's a lot of STEM concepts that you can learn from robots. And in the curriculum that I'll look at a little bit later, there's many different activities that can be tied directly to government mandated standards and achievements in sciences and math. And typically when you're working with robots, it's about collaborating, getting different people with different skills together to creatively solve some problem. And on the problem side, it can range from competitions to finally getting this robot to do something, to figuring out how to make it look good. Here's a couple kids and a parent volunteer getting a robot and figuring out how to attach something to it so that it doesn't fall over. So solving center of gravity type problems and going from there. So demonstrations in physics, engineering, you take robots, measure things, graph them. Challenges, we've all seen the different robo competitions, sumo bots competing, line following, micro mouse. It goes down to 5, 6, 7-year-olds that use robots and dress them up and dance with them. I'll show you a video of that later. And all the way up to first and on where you're taking university, high school, or professional engineers and coming up with some really cool ways of solving problems. So currently, there aren't that many robots in schools. They may have a basic stamp. They may have a computer lab where they get students to graph equations, but typically there's not a robot lab. So far it's been difficult. So for teachers to introduce robots in their classroom, it's been difficult, both for the teacher and for students to get the most out of it. Robots have been limited in functionality. If you just have a basic touch sensor, then there's not a lot you can do. If you have cameras and fiducial markers and OpenCV and wireless and everything else, then there's a lot of power and a lot of flexibility that you can do with those types of robots. And robots used to be expensive, so hundreds of dollars, thousands of dollars, and expensive not just in dollars, but also in time. So it took a lot of effort, a lot of time to get a robot to do something simple. And that's the one, we're really focused on all three of these, but especially on making it easy for the new teacher, novice teacher who says, hey, you know, robots could be something good. I don't have 2 weeks to figure out how this robot works and how to integrate it into the state government curriculum, but let's figure out how to get it in there. So robots aren't difficult. They're not limited with today's low-cost sensors, and they don't have to be expensive, time-wise and money-wise. So I'm from New Zealand. I have to show the picture of a sheep. I'll show this every year. Gets better every year. And so here is 12 blocks and T-Bot at my daughter's primary school. Mac computers and the T-Bot, I'm here, but they're running the class there still. So there's a bunch of T-Bots there. The kids that I taught last year, and I took them to a couple competitions, they're now teaching the kids from this year. So it's starting to grow. There is a couple other schools in New Zealand that have side licenses for my 12 blocks program and are starting to take the curriculum that we've developed and use that to teach robotics and science to their kids. So I always like I like the challenge of the HPRC vibe that demos don't work. So I'm crossing all my fingers. I've made all my sacrifices today, so we'll see if things work. The T-Bot does have a nice feature in that it is USB charged, so I should not have a battery problem today. So that's something you could add to your robots. So just a very brief overview on this one. I'll give a bunch of demos. We'll see. And I'll sort of start at the lower end of sort of primary school kids, where we're not doing too much of advanced sensors, where we're just doing start simple, get them interested, show them what robots can do, and give them the sexy stuff, give them the lights, the sounds, movement. But still, at that level, by not needing to focus on syntax, grammar, and and the language part of computer programming, we can focus on advanced concepts like multiprocessor, doing multiple things at the same time, functions, so being able to abstract your code and make it reusable so that other kids can take advantage of what you build, loops, simple sensors like the microphone, and then simple events and condition programming. So let's go start off in 12 blocks. So here's 12 blocks. And all this is sort of me building it, coordinating people all over. So there's a lot of people I have to be thankful for. Chad especially is the main designer on the T-Bot, and just sent this guy from the factory. It arrived yesterday. I have had a T-Bot a year, but this is the one that's the official one. So 12 blocks is this visual language. I didn't invent it. It's been around for 20 years or so. And the concept is that you don't have to memorize a lot of language. You don't have to remember if you're using squiggly brackets or if you need a semicolon. You're just focused on the programming part, the logic part of what do you want to do today. And you have a library on one side. There's different libraries for different processors. So 12 blocks supports the Arduino, the basic stamp, all sorts of Parallax propeller products, the Mindstorm NXT, the Pickaxe, and I'll use the library for the T-Bot that I have here. And in this library, there are a number of sections. And there's 200 some blocks, I haven't counted lately, that range from looping conditionals to the terminal, so you can print your hello world and interact with it, to sounds where you can do speech synthesis and playing wave files, to plucking like a harp, sounds pretty good, or the sine waves that we've grown to love for the last 60 years or so that we've played. Tones, motion, so moving and using servos to move things, sensing, so ADCs, and depending on the hardware, you'll get different blocks, but it's a complete language, variables, arrays, strings, random numbers, functions with refactoring and local variables. So it's a very complete language that people can write almost anything with. There's other visual languages out there, Scratch, App Inventor, that are typically much more limited in terms of arrays and strings and functions, and it's not just gluing some blocks together, but it's giving you everything that you could do in the base language. So let's start very simple. I like to start with a blinking LED, and first thing is we'll just have a red LED, and here's our red LED. It works at least, right? Yeah. Okay, so there is our green LED. It work? Yeah. Okay, so two things work. Okay, we can put this in a loop. So really quickly, you take a repeat, and now here is a green one, and we'll alternatively go between red and green. So we'll flash those so that you can see it. And this is where students sometimes say, "Well, let's not put a weight in there," and then it blinks so quickly that they can't tell. So it's the first challenge of why is it going like this? This is 1,000 milliseconds, so it's 1 second. And here we can run this. Now it's blinking red and green. Yeah. And kids don't have a lot of attention these days, so instead of having to recompile all the time, you can just change these numeric parameters. So now instead of waiting a second between each color change, it's taking 200 milliseconds. So there is our light experience for kids, and it's just blinking away. I'm going to start multi-processing. There's actually 2 chips on there, so there's an Arduino in here, as well as a propeller, and the propeller with the open source code. Come on, you clapped before. Open source. Is also a USB host controller. Yeah. And so you can stick, for example, a Bluetooth chip in there, and then you can control it over USB, over Bluetooth, or you can hook it up to other USB slave devices if you wanted to. But now we're going to go from lights to some sounds. So we're still going to do the lights because we like those. And one thing that we can do is we can play the standard tones. So we'll do a tone. So a tone, you specify the frequency and how many milliseconds. Everything's in milliseconds to keep it simple. So here's 2 tones, a low one and a high one, and they'll stop right away. Okay. I'll be quiet. Okay, beep beep. Okay. If we want to play something more complicated, we can do lots of notes like that and look up what a major C is, or we can use this play score. And so kids that read music are like, oh, okay, so C, C, G, G, and then it starts sounding something like this. Okay. My dad likes to say that this is not just one song, but there's Haydn who composed it, and then there's 4 or 5 different usages of it. There's also plucking. So this is just a sine wave, which we've heard forever. This is a mathematical way of simulating like a harp or a stringed instrument. And again, to the student, they don't need to know about allocating things on a stack or including objects from a library or anything like that. They just need to know, I want to do something with a sound, and so I'm going to go to the sound section of 12 blocks and pull that block out and connect it somewhere. There's no, I can't stick this to the top and I can't stick it on the side. It tells me there, it sort of highlights, and then it sticks on. So give this to a 5-year-old who's able to read, and they can stick these together. They might not have a good idea of what they really want to do, but if you give them some hints and guide them, then pretty quickly they're able to put something like this together. And they're focusing on the logic of programming and not on the CLK, FREQs, and the pound include and other things that we sort of grew up with. Sort of here. Yeah. So it's just a different way of doing music. And yeah, so there's lots of blocks. I'm not going to go through all of them. We will repeat this periodically, and then in between we'll wait a little bit, so we don't do it all the time. So, and you notice that without having to do complicated interrupts and figuring out how to interleave our processor timing, it's still blinking the lights at the same frequency that we initially set up, and it's doing the music. So nothing complicated. I just have 2 start blocks. And if I want another stop block, I can put it out there. But I'll do something a little bit different. I'll do a when block. And I could do when true, or I could do when a button is pushed. So T-Bot has a couple buttons, and here is a left button pressed. So I can slide that in there. These yellow parameters regions, I've already shown that you can click on them and edit them while the program is running. But you can also type long expressions in there. Other visual languages like to make everything a block, and then if you're trying to do a simple expression where you're trying to add and multiply and compare, it means you're taking 20 blocks and dragging them, which might be fun for very young people, but to us engineers, it's better to just have a text box and just type. So you can type in the yellow area, and you can type expressions and variables and go from there. So here's our when left button is pressed. We've done our lights, we've done our sounds. So now we need some movement. Need to make sure that this guy's turned on. There. When you plug it in with USB, it's charging and it's powering it, but you can turn it fully on, and then the motor is on as well. And it has a pretty advanced power system where it charges the lithium-ion battery, but it also boosts the voltage, so it can go quite fast. And we'll just do some motion right now. moving forward and turning. At some point we like to get away from just this procedural where we're doing one block after another and get into functions. So let's put that in a function instead. So here is my function. And we'll take these into the function. You notice that as soon as I moved the function header out there, it created a function caller. So that's how I call it. And I can refactor, so all these advanced words, and I'll call this dance. And because I called this block dance, this one up here changed its name to dance as well. And I can also give it some arguments, so I can give it a how far and how much to turn, so I'll do X, Y. And then the block up here gave me those parameters as well. So I can just type things in here, and I'll just type so it's going to move forward for 1 second, and then turn for half a second. Okay. Nice thing with visual languages is that you're not restricted to one dimension where you're scrolling up and down all the time, but you can put things side by side, and if you want to keep something for later, you can just leave it on the bottom somewhere. So it's very nice. I programmed all this in C#, and so I have to scroll up and down all the time, and then when I get back to 12 blocks, I'm like, yes, this is more what it's intended, that you can drag back and forth, and you can see all of it on one screen. If you want to, you can save this and include it, and so that's how you get into bigger, more complex solutions. And you can also go on the base language, so the underlying C code that's powering the robot, and create new functions and import them. So you can add blocks as you want.
You have
So
to put the globals into the move and turn on the dance.
So dance has 2 parameters. Oh yeah, okay, sorry. Yep. That's what you want. So these are the parameters for the dance function, and I'm going to use them in there. And just so I'm not cheating, I'm going to go 2 seconds forwards. Okay. Go. And now let's see if this works with motors and lights. And okay, so it's still playing that. It's waiting a second in between. It's doing the green light, red light, and I can still change this, so green for a little bit longer than red. There. And now I'm gonna press that button, and it goes forward and turns. So. Okay. Let's see, so we can hit stop. Yep.
Is the fact that you're running different segments of code, because you're using a propeller and segments, the processor in 8 boxes?
So I'm a huge proponent of a propeller as opposed to Arduino or other things, because it doesn't have interrupts and it has these 8 cogs, and so that makes it very easy to do this style of programming.
And each one of these is running in a cog?
It's running in a cog, and yeah, so you can have a lot of power, so approximately the power of an Arduino, but you have 8 of them on one chip sharing memory. So the propeller is very good.
What happens when you have more than 8 blocks?
It'll tell you that please don't use more than 8. You can simulate this on other systems, but it'll take more horsepower because there'll be switching time and so on. Yep.
So you can put up to 8 blocks, and the propeller will be able to run it?
Yes. Some of these blocks are different. So the when block is using the event cog, which is running separate from this. So, but let me keep going with this. So you notice that there is something funny on top, so there's Legos stuck on top. So when I go into classrooms, not everybody wants to be a programmer when they grow up. And some kids like to dress up things, some people like to play with mechanics. And that's fine, that's good. It's still good to get everybody working together as a team And so what we do is we have some people who use Meccano, Vex, or Lego to build things on a robot, or take styrofoam and then build things and put feathers on it and color it, put servos on it. Some people like music and then like dance. So one of the things I really like doing with younger kids is Robo Cup Dance, where kids have to take multiple robots and they're confined to a certain area, 2 by 2 meters, 6 by 6 feet. And then they take these multiple robots, dress them up, use servos, use LEDs, and they choose some music, 2-3 minutes long, and they get up on stage in front of hundreds of people in these competitions, and then they let their robots run. Hopefully they don't have battery issues. And they dance a little bit, and they choreograph what they're doing, and robots are autonomous. They're sitting there on the floor, and 2 to 3 minutes doing something. And some of this may sound simple, but it's not. You're in the real world. You're on carpet one day, you're on different surface another day. And so I'll go into my next demo, which is actually a video. Makes it easy for me. And show you what we ended up with last year. So I took about 8 weeks of coming back from here and showing these kids the T-Bots, and then we went to the regional competition and then flew up to the national competition. And this is with primary school kids. My daughter, 5 years old, was the youngest. Next youngest was 6 years old, 7, 8, 9 years old. And this is what they came up with. I don't have audio. I'll make it as loud as I can on here. But it's basically this Maori song, and overall the theme is that there is a Maori, a moa bird, which is extinct now, but used to live in New Zealand, and the moa bird was running around, enjoying life, flapping its wings and lighting its eyes. And then after a while, the moa hunter came out, moa hunter with a spear, and was going after the moa, and then started stabbing and killing the moa bird. And then the moa bird went into its dying throes and juttled back and forth, and the eyes blinked more, and then the moa died. And very sad. But very happy for the moa hunter, who then cheered and moved around. And since this is a kid's story, the moa then came back to life, and slowly the eyes, pulse width modulated, dimmed, gradually got brighter and brighter, and then the wings moved a little bit and moved more, and all of this in 2.5 minutes, all of it programmed by 5, 6, 7-year-olds using 12 blocks and using the T-Bots with styrofoam things on it. Okay, here we go. Okay. That's my daughter Anya over here, the cute one. All right. So that's young kids just starting out, and as you go up in age, you can build on that foundation with more sophisticated behaviors. So you introduce variables and advanced functions with local parameters, sensors that really tell you more than just one thing, and control theory, pit loops, state machines, and all of this also at the sort of last years of primary school, beginning of high school. So very advanced stuff, but stuff that you can handle because you can make it very simple. So let's go into some of that.
You're
again.
demonstrating state machines with 12 blocks?
Yep. And I'll start off with a state machine, just since I got a question. Normally state machines, they're wonderful to look at in textbooks because you have these nice states and then transitions, and it's beautiful on paper, and then someone says, okay, I'm going to write this in C, and uses some switches and so on. But within minutes, it doesn't look that pretty anymore. Right? So let's see how we do state machines here. So there is a block that looks like a start block. It has one of these triangles on top. You can't put anything on top of it. And it is a when in state block. And I'm going to put awake here. So when it's awake, and since everybody likes terminal things, I'll do this. So when in state there, print hello world. How about it also increments a variable, so change x by 1, and then an if, so it's a condition, if x greater than 10, then we're going to change states. So here is the state machine, and so now we change it to sleep. And we're going to have another state over here, and this one is sleep, and this one then prints text. Okay. And this one also changes x by something, and when x is greater than 20, it sets it back to awake. And just so that this actually works, I'm going to set x back to 1 over here. So looking at this, it's very easy to see what state you're in, and it's very easy to see the state transitions. And what we still need is we need some way to actually run this, and so there's a start block, and then repeat, and so continually we're going to wait a second just to slow it down for us and run the state machine. And we can have multiple state machines, and so we need to keep some variable that manages that for us. And that's the strategy, or that's the Bob state. And we're going to initialize Bob, so we use a variable and start with that and set Bob to awake. Okay. This is even more calling to the demo gods that this works, because I haven't tried this for a while, but let's see. So this is computer science code running on the T-bot. I do have a values, which gives you this oscilloscope type control and graphs, real-time values there. We'll look at that later. There's also this logic state analyzer, and shows you the states of the pins. So if you're doing experiments, you can see what pin is high and low. And then what we're going to use now is a terminal. Okay, fingers crossed. Okay. Okay, so it's first awake for a little bit, and it's printing out hello world a couple times.
How come that's not like happening instantly? Is there a speed limit, or?
how come it's not happening instantly? So it has to compile, it has to create the backend code and compile it and load it.
No, I meant, but how come the state machine is running slow? Like,
Because I have a wait 1000 in the loop that's doing the state machine.
Oh, duh.
But good question.
Okay.
If I took that out, it would go over. But you can see that he's alive, he's sleeping and being awake. Okay? So pretty nice state machine demo. Yeah. Yep.
Is that one processor or three there?
This is one processor. That's what I said, that these start blocks, they're not all cogs. You can use many state machines, you can use multiple state machines and run them all in the same cog. So yes, a start block uses up a cog. Most of the others don't.
Maybe you just kill the weight and let it run full tilt. Is that good?
All right, if you really want to.
Yes.
Okay. There is a megabit per second connection through here that's sharing the I/O states of the propeller, plus sending the terminal data back and forth, plus sharing the variables, the global variables. So at any point you can look at the global variables, and you can also change parameters in your running program. So let's do some of that. So I'll start a new one, and so I'm going to do just a super simple program. I'm going to repeat and continuously set the value of x to a sensor value from the T-bot. So the T-bot has all sorts of sensors, so we can use the get docket in there. And it has proximity sensors and line detector sensors and a microphone. Let's do the let's do the front left sensor first. And then we'll do the front right. No. Okay. So here is the front left sensor. Here's our timescale knob. We'll set it to something that we can see in human scale, which is 500 millisecond per division. Right now, it's giving us a big value because there's nothing in front of it. If I put something in front of it, you can see that value changing depending on where my my hand is. Yeah? Okay. My dad said that you guys like seeing things like this, so I'll do more of this. So we can do that with all the different sensors. I'll show a really cool one. We can read the motor current and battery voltage and USB voltage every 500 microseconds, and very nice detailed. So when we turn the motor on, we can see nice spikes on there, and so it's wonderful for debugging things, or wonderful for seeing if you're climbing up a hill, or in the physics class putting a weight on here and going back and forth and seeing how much motor current is being used, and using that as a scale. So next thing, you guys like graphs, so we'll do another one, which is to use the microphone. And we've done human scale, which is sort of a 500 millisecond per division where I move my hand, it moves. Now let's do a little bit faster, and I'll turn this guy to millisecond, yeah, and then I'll do the best singing I can. So some people still have oscilloscopes, and we can trigger this. So I just clicked on here, and that gave me a rising edge trigger, and I can move that up and down and all that. And now when I sing again, it'll be nicely triggered, and we can measure the frequency and all that. Okay. And we can turn that in, yeah, so, okay. So oscilloscope is sort of built in there. We can, so one of the things that was useful there was that we now know that even though I sing so beautifully, the amplitude is typically in this 100, negative 100 to 100. It's AC coupled. But if I clap, there is these big spikes that are about 1,000 or more than 1,000. So one of the things I can do is I can use the when block, and I can do when read microphone greater than 1,000. Who knows what this will do? It starts something when I clap, so here is the clapper. And it looks really good when I do this. So here's a super complex program, right? Yeah. So it's 3 blocks. I called this 12 blocks because I think within 12 blocks, so dragging 12 blocks out there, you can do just about anything. But okay. So here we go. Be very quiet. Okay. Okay, so we've done human scale, we've done the microphone. Now let's do like PID stuff. Yeah? I brought this good book here, and I'll place it there. And I'm doing all this from scratch, right? I'm not loading files or PowerPointing things or showing videos. So let's do a start. We'll do a repeat, and we're going to set a variable to our trusty front sensor, which is the get front. So set x to get front. And if we look at this, we notice that for this distance, we'll do sort of that distance, it's at about 1,000. So we're going to put 1,000 behind there. And now we're going to drive the motors, set motors, X. Okay? So the left motor is getting X, and the right motor is getting the value of X. Right? And we're setting X to a measurement, a distance measurement, adjusted by some desired value that we want. So what does this give us? I don't know. Press the run button. Okay. Nothing. Okay. But let's see. It's following me. Okay. So it's not using PID, it's just using the P part, the proportional part of a PID controller. 12 blocks has a PID controller for us, so let's go into our library, and it's under variables, and here is our PID response 1. And we can do another variable for us. And I'll also take out the restrict so that we don't overdrive the motor. And we're going to set Y. And one nice thing here too is that we see the value of X, and we can graph it there. Right now it's just noise. But when you move, you get these nice stimulus response curves. I'll make it even slower. There? Is that a pretty nice stimulus response curve? Okay. So here we go. Set Y to PID response to error, and error is just X. And we're going to start with P set to 100 and a little bit of the proportional integral derivative, and these are the constants that the PID function takes in order to give us a better response. And then we're going to, we could do all this in one line if we wanted to, but I'm using 3 variables so that later on we can look at what each one of us is doing. And we're going to set Z to restrict y between negative 500 and 500. All right. Now let's give this a go, like we say in New Zealand.
Set motors to Z.
Set motors to Z. Very good. Thank you. Lego Mindstorm also has a block-based thing, but all the properties are hidden behind the blocks. So I couldn't do a separate demo because you would just see blocks with nice pictures on them, which don't help anybody and no one can understand what those pictures mean. And all the parameters are hidden so that you have to right-click on the thing. So I think this is better.
How many variables can you have?
Unlike the pickaxe and other things, the propeller has lots of memory, so lots of variables, and lots of arrays and strings and everything else, floats. So here's the PID controller with this. So it's moving up and down. We're doing a, the only thing that didn't make it to this one is that there's a plastic injection molded shield on the bottom which has a nicer wheel on the bottom, a nicer, yeah. And so this one moves up and down and that's why it isn't as nice. One more thing that we can do with this is since we have 2 sensors and 2 motors, we can get it to turn. So I'm going to try to do that too. And I'll use another variable for Tony. I'll even name it after him. Tony. Okay. And Tony, we're going to set to the difference between the front left and the front right. Okay. And we'll pull the front right here. And when we run this, let's see what sort of value we come up with. Okay, so it's pretty close to 0, depending on where we are. Yeah, it's good enough, right? Okay, so we're just going to take that, and hopefully all our signs are right, and we're just going to add and subtract Tony from the motors. Okay. This is as complicated as I'm willing to go on the stage. Okay, so it's still now tracking somewhat, but now, aha, it's also using the IR sensors and the magic Tony variable to turn with it. It also has proximity out the sides, so I'm using 2 proximity right now to stay roughly aligned with my book here, but you can also imagine for micro mouse or so that you stay aligned with the walls. Okay, so this demo was all about using variables and PID response and using our trusty oscilloscope here. You can see it's sort of oscillating in states. I could change the parameters, but I won't right now.
You got filter blocks?
Hmm?
You have a filter block?
No, you have to build that one by yourself. So not in there, but it makes a lot of sense. So I'll get it. All right. So I'll stop that and go back to my presentation. And so more advanced than dance. I just switched. That was Microsoft working. So the next stop. So some kids are doing the dance competition where it's all about blinking lights, but it's all very procedural. There's another competition called the Rescue Maze competition where there's line following, but it also involves state machines because you're line following for a while. And after a while you get to an area where you then have to search for the princess and you push her out of a given area. So the robot has to do different things at different time, and it has to line follow and it has to look for things. And so I took a team up there. They also made it to nationals with the T-Bot that were doing the rescue maze. And I have a very short video. So that's it. Should we see it again? So it made it all that way, and there's actually little indicators on the left and right sides that tell you which way to go. For example, there's a circle, and so there's a green square here and here, and so you line follow, and then you recognize that there's a green square, and based on that you turn one way or another. And then once you get to this green area, you switch over into a different mode where you're then looking for a Coke can and pushing that out. Okay.
Question?
Yep.
I noticed your parameters seem to be nicely matched. Is there a scheme behind that where you make some unit value to, like motors have a value that matches the value of the sensors, which matches?
My dad's a physics guy, so I like matching units and matching numbers too. But behind here and behind all the different platforms is code that actually implements what you just drag around. So behind each one of the blocks there is C code or spin code or basic code that implements that block. Typically sometimes it's simple code, so it's just a simple function like a PID controller. But all of those also have local variables. Sometimes they require additional stack space, sometimes they require additional objects, sometimes they require setting things all over. So what I'm trying to do is, instead of you having to remember that to get speech synthesis working, you need all these pieces, with 12 blocks it's just one block, and then you type it in there and go. And the parameters are as simple as they need to be for the common day, everyday occurrence. I didn't show it, show it now since I can. You can view code and either as text or as the lower level language. So for spin, this is my other program called Viewport, and in Viewport you can edit code, and there's a Visual Studio-like line-by-line debugger and breakpoints and real-time graphs. So it's sort of 12 blocks on steroids with a full oscilloscope with measurements and cursors and a full logic state analyzer and video stuff, and yeah, so there's lots of stuff there. But you can look at the code, and this is the code that was generated from this program that we had here. So if we're lucky, we'll find Tony.
So this is port from you, or is this still
You post that
12
to the list?
So there is Tony.
That's Tony.
Right?
Now, can you reverse this? So if you edit this code, you can't go back.
Of course you can. We're getting very advanced for my liking, but I will try it anyway. I'm going to change this -500 to -200, and I'll leave it at that. And now I'm going to save this file. This may not work, but let's see. And go back to, no, I didn't pick it. Oh, let me try one more thing. Again, it might not work, but I'm going to save this file before I go back and forth. So Tony. Okay, and this one, put it out of here, and I'm going to do this view code again. I'll use my one excuse that this was working 2 hours before.
Can't blame the batteries this time.
So -200 over there. Okay. Ha! Okay, so I switch back, I alt-tab back to 12 blocks, and now 12 blocks knows that the file that it just showed me was changed. And so it says, do you want to reload it? And now I'm going to press yes. Ah! And so there is the -200 that we changed. So this is not meant to take arbitrary code in your lower level language and always translate it perfectly back into blocks. So it's not a tool to convert any language into colorful blocks. What it is intended to do is to familiarize students that none of this is magic. that these blocks, they're not magic, but once you're comfortable programming with them, and once you're happy with this, then the teacher can say, well, look,